Chapter 6, Thread-Safe State, Atomic Classes, Locks, and Concurrent Collections. Chapter 6, Thread-Safe State, Atomic Classes, Locks, and Concurrent Collections is about protecting shared mutable state in concurrent Java systems. Threads, executors, and virtual threads help us run work concurrently, but they do not automatically make shared data safe. Once two or more threads can read and write the same state, the system needs clear rules for visibility, atomicity, and coordination. The first principle is simple. Avoid shared mutable state when you can. Immutable objects, local variables, message passing, and request scope data are easier to reason about than shared structures that many threads update at the same time. But real enterprise systems still need shared counters, caches, queues, registries, deduplication maps, rate limiters, and coordination flags. That is where Java's concurrency utilities matter. A common beginner mistake is thinking that volatile makes everything thread safe. It does not. Volatile gives visibility guarantees. When one thread writes a volatile value, other threads can reliably see the latest value. It also helps establish happens before relationships. But it does not make compound operations atomic. An increment is not one operation at the machine level. It is read, modify, and write. Two threads can still read the same old value and overwrite each other's work. So volatile is useful for simple flags and publication patterns, but not for counters or multi-step updates. Atomic classes solve that problem for simple state changes. Atomic integer, atomic long, atomic boolean, atomic reference, and related types provide lock-free atomic operations using compare and swap style mechanics. They are excellent for counters, state transitions, simple flags, and reference replacement. Instead of locking a whole critical section, the atomic variable updates itself safely as one indivisible operation. Atomic reference is especially useful when the state is not just a number. It can hold a reference to an immutable object and replace the whole object atomically. That gives a clean pattern. Keep the state immutable, calculate a new version, then swap it in atomically. This can be much easier to reason about than mutating several fields under a lock. For high contention counters, long adder and double adder are often better than a single atomic number. A single atomic long can become a bottleneck if many threads repeatedly update the same value. Long adder spreads updates internally and combines them when the value is read. That makes it strong for metrics, counters, and monitoring values, where extremely frequent updates matter, and exact instant consistency is less important than throughput. Locks are the next level of control. The simplest lock in Java is synchronized. It is built into the language, easy to read, and often good enough for small critical sections. A synchronized method or block protects a region so only one thread can enter it for the same monitor. It also gives memory visibility guarantees. For simple coordination, it remains a valid tool. Reentrant lock gives more explicit control. It allows try-locking, timed lock attempts, interruptible waits, fairness options, and multiple condition variables. This matters when a system needs to avoid waiting forever, separate different wait conditions, or express more advanced coordination than a basic synchronized block can comfortably handle. The trade-off is that explicit locks require discipline. If you lock manually, you must unlock reliably, normally in a finally block. Conditions are useful when threads must wait for specific state changes. They are more flexible than the classic wait notify model because one lock can have several condition queues. For example, a bounded queue might have one condition for not empty and another for not full. This makes coordination clearer and avoids waking threads unnecessarily. The danger with locks is not that they are bad. The danger is that they are easy to misuse. Holding locks too long reduces throughput. Calling slow I/O while holding a lock can block unrelated work. Acquiring locks in inconsistent order can create deadlocks. Locking around too much code can make the system technically safe, but operationally slow. A senior engineer should keep critical sections small, protect only what must be protected, and avoid mixing locking with long-running or remote operations. Concurrent collections solve a very common problem: safely sharing data structures. A normal hash map, array list, or hash set should not be mutated concurrently without protection. Concurrent hash map, concurrent linked queue, copy on write array list, blocking queue implementations, and concurrent skip list map provide thread-safe alternatives for different access patterns. Concurrent hash map is the default choice for shared maps in many backend systems. It supports high concurrency access and atomic operations such as compute, compute if absent, merge, and put if absent. These methods matter because they avoid unsafe check-then-act patterns. Instead of checking whether a key exists and then inserting, both steps can be performed as one coordinated map operation. Copy on write array list is useful for read-heavy, rarely updated lists, such as listener registries or configuration snapshots. Every mutation creates a new copy internally, so writes are expensive, but reads are simple and safe. It is a poor fit for frequently changing lists, but excellent when reads dominate and iteration safety matters. Queues are central in concurrent systems. Concurrent linked queue is useful for non-blocking queue behavior. Blocking queue implementations, such as array blocking queue and linked blocking queue, are useful when producers and consumers need back pressure. A blocking queue can naturally slow producers when capacity is full, which is often more useful than allowing memory to grow without limit. The deeper point is that every tool has a cost model. Atomic classes are great for simple, independent state. Locks are useful for coordinated multi-step changes. Concurrent collections are useful when the shared state is a data structure. Immutability is often better than all of them when the model allows it. The wrong tool can be technically correct, but still slow, brittle, or hard to understand. Thread-safe code also needs testing. Normal unit tests often miss concurrency bugs because race conditions depend on timing. Still, tests can help by isolating state transitions, validating invariants, and using repeated or stress-style execution for risky areas. For highly sensitive concurrency utilities, tools such as JCStress can explore interleavings more systematically. At a practical enterprise level, metrics, logs, and production observability also matter because contention and deadlocks often appear under real load. The senior takeaway is that correctness comes before performance. A fast race condition is still wrong. Start by making shared state safe and understandable. Then measure contention and optimize only where there is evidence. Prefer immutable data. Use atomic classes for simple state. Use locks for coordinated critical sections. Use concurrent collections instead of manually protecting ordinary collections. Thread-safe state is not about sprinkling concurrency utilities across the codebase. It is about choosing the smallest clear mechanism that protects the invariant. When the invariant is clear, the synchronization strategy becomes much easier to design, review, and maintain.